Hello everyone, we're going to begin our basic chemistry notes with this presentation. We're going to cover elements, atoms, and the basics of the periodic table and interpreting it. So let's get a head start. So here we're going to first begin our unit talking about elements. Now if we give a standard definition for elements, it's going to be a pure substance which can't be broken down any further by any chemical means whatsoever. So it's one item, it's pure, meaning that it's not made up of different things, and there's no way to naturally break it down by any chemical means into smaller substances. So if you look up here at the top, we have what? Helium atoms. That would be one individual specific element. And then over here, what we actually have are oxygen atoms that we breathe, and we would actually write that as O2 because you can see there's actually two atoms of oxygen that are bound together. And over here, obviously, we have some water. We have some H2O. All right, where we're going to have one oxygen, which would be this one right here, and then the two hydrogens bound together. All right, that lets us make larger materials called compounds, but right now our focus is on the individual building blocks, the elements themselves. Now, total that we know of right now, there's roughly about 118. All right, and of those 118, there's about 98 that are known to be naturally occurring. Now, what I mean by naturally occurring is you can go out into the world and find them. All right, if they're in a gas state, you can find them. You can dig underground and find them in rock or anywhere else in particular in the world underneath the oceans. You can find these elements naturally. Because some of the elements, actually, of the 118, some of them are man-made, right? Not purposely, but some elements like plutonium, which is used in nuclear reactors and used to make atomic bombs, is actually a byproduct of uranium being used for fission in nuclear power plants like we have here in Limerick. So some of them aren't really naturally occurring. They could be man-made through our processes, but most of them are naturally occurring that we find out in nature. And again, every single one of them that we know of currently is listed, all right, and identified on the periodic table. So again, moving forward, an element is a unique substance which can't be broken down any further. Again, if we look at some examples here, we have a copper pot over here. All right, obviously it's huge, it's big, it's solid, but if it's actually a pure copper pot, every single atom is the same element of copper. And again, copper would be what? Cu. If I have some pure carbon that, let's say, hasn't been compressed yet into a diamond, again, carbon, the symbol would be C. Again, you would just have individually, see them all, every single little atom / element that is bound together to make up this substance up here. And then the same thing happens for gases. Gases usually are lighter than atmospheric air, but they don't have to be. They can also sink, like carbon monoxide. If you ever heard of that poisonous and deadly gas that could come up into your house through your heater or perhaps your water heater, they would be heavier, meaning that all of these individual atoms / elements that you see would be much closer together. They'd be like this, but they wouldn't be directly bound together. That makes them more dense since they would be closer together, and that's why it would kind of sink and float to the bottom of your ground. Again, helium would be He. So it's important to understand that all of these materials, if they are pure, they will only really be made up of that one specific element that they're comprised of. Now, if you notice, I kept using the term atom or element, when in fact, an atom or an element, those two terms can almost be used interchangeably. All right, so what is an atom? All right, you've heard of an atom before. It is the smallest part or particle that makes up an element itself. Now, I just told you that an element can't be broken down any further, but that doesn't mean it's not made of something. So think of it like this. If I have a square here, and let's say that's an element, well, that square or that brick still needs to be made up of little dots, and those will be the atoms. That'll be really close together, and they will have the exact same properties of that element itself. And it all has to do with what they're made of, those particular atoms, in reference to the element that we're focused on. And that leads us then to the atomic structure of an atom that you can also see up in the diagram up above. All right, every atom, again, which is a building block of an element, is going to have a very specific structure and breakdown. Every atom is made up of several what we call subatomic particles. These particles are even smaller than the atom itself. All right. First off, though, we're going to start with atomic structure with the nucleus, which is always at the center of an atom. So if I were to circle it up here in the picture, this would be the nucleus. Now, we're going to have three key subatomic particles, which you can also see listed up top in the diagram. First, we're going to start with a proton. Now, a proton is a small, tiny particle that we're going to find inside the nucleus. It's only ever going to be inside the nucleus, and it's going to have a positive charge like you would have on a magnet. Now, we'll also have what we call electrons, which are very small subatomic particles that are making up an atom, but they're not found inside the nucleus. All right, they're going to be found outside, and they will have a negative charge. So again, up here, an electron will have a negative charge. A proton will have a positive charge. So outside, you can see negative charged electrons, and inside, you're going to have these little positively charged protons, if I can actually get you to see it there. And then finally, there is a third subatomic particle, and those are called neutrons. They have no charge. They're neutral. All right, so you could just write them as like 0 if you wanted to. All right, sometimes with like a little squiggly line inside. They have no charge whatsoever, so they're not attracted or repelled by other subatomic particles. Now, the structure of an atom is highly, highly stable. They don't break down normally. Now, they can over tens of thousands or millions of years, but it's normally a very, very slow decay. And when I say decay, maybe the atom loses an electron or two here and there over thousands of years. But that's it. It's not just going to blow up and fall apart. All right, but notice what I just said, blow up. This atomic structure is so stable that you will not just randomly have nuclear bombs or atomic explosions going off. But what you got to think about is, inside the nucleus, this little tiny, tiny thing, you have protons that are positively charged, moving inside nonstop, almost at the speed of light, which is roughly, I think, like 186,000 miles a second. That's really fast. And they're positively charged. But outside here, little star, you have your electrons. And they're negatively charged. Well, guess what? They're attracted to the positive protons. So you're going to have electrons that are continuously orbiting around the nucleus, almost at the speed of light, trying to get into the protons who are trying to get out to come together with the electrons. They never do, naturally, because if they did, you're going to have, even though they're so tiny, you're going to have a proton moving towards the speed of light, come in contact with an electron near the speed of light, and when they were to come into contact, you're going to go boom, and you're going to have an atomic explosion. All right, just like the bombs that were dropped during World War II on Nagasaki and Hiroshima. And that was just one particular atom being split at that time. One atom. That's it. To release this huge amount of energy. It's insane. So atoms don't normally just break apart. All right, their structure is perfect for maintaining stability. So again, where are we at so far? Elements are the smallest things that cannot be broken down any further. All right, they have unique properties, but once again, they're also made of smaller particles called atoms. Now, when we look at the periodic table, we're going to see elemental symbols, which will have a number up top and a number below. The number up top is called the atomic number, and it's going to be equal to the amount of protons in a nucleus. So think of it like this. This top number over here for carbon, 6, really just means, by definition, how many protons that element has in its nucleus. However, every single atom on the periodic table is also considered to be neutral. So by default, it should also have the same amount of electrons. All right, so that's the key to remember. So carbon has 6 protons by definition, but it also has, since it's neutral, 6 electrons that are orbiting around its nucleus. Now the bottom number, the atomic mass, is what we call it. Think of mass. It's what really weighs the atom down. It's what's going to be inside the nucleus. All right, we're always going to, for our purposes, if it's 0.5 or higher, we're going to round up. If it's 0.49 or lower, we're going to round down. So for us down below, 12.011, we would consider that to be just 12 for our purposes. Now, this number equals the amount of protons and neutrons added together inside the nucleus of that particular element or atom. All right, so what we have here is this. For carbon, we know it has 6 protons, because that's what its atomic number is. Since we know all elements now are neutral, it should also have the same amount of electrons. Do a little negative symbol there. And then if I want to figure out the number of neutrons an atom has, all I got to do is take the mass number, which is 12 in this instance, subtract the top number, all right, which is the atomic number, because what I'm trying to do is I'm trying to cancel out these protons, right? Just so I can get to the neutron number. And 12 minus 6 in this instance is 6. Ugh. 666. Devil symbol, right? This is kind of weird that carbon actually has that particular combination. But that's just the way it works. So let's do some more examples here. If I look at nitrogen, first off, I'm going to round down that mass number, right? Its atomic number is 7. Its mass number is 14. Its number of protons is the atomic number, so that's 7. Those protons should always equal the number of electrons, so that should also be 7. And then neutrons we're going to get by taking the mass number, subtracting away the atomic number, and in this instance we get 7 as well. They're not all like this with the same 3 numbers. And we can look at magnesium. All right, magnesium has the atomic number of 12. That's the top number. And then it has the mass number of 24.305. So for our purposes, we're going to round down, and we get 24. All right, how many protons it has? Well, that is the atomic number by definition, the top one, so it's 12. It's neutral since it's on the periodic table in this form, so it have the same amount of electrons. And finally, what we have is the mass number, again, being 24, which is both protons and neutrons added together. What I want to do now, again, is I want to take away the amount of protons. So I want to cancel these out, just so I can get to the neutron number. So I'm going to take 24 minus 12, which is the top number. And once again, in this instance, I gave you 2 simple examples here, is 12. All right, so for this evening's homework, you're going to do a worksheet that's very similar, just getting you used to understanding what the symbolism is for these elements, which are made of atoms. The top number is the atomic number equal to the number of protons, and the mass number, the bottom number, is equal to protons and neutrons added together within the nucleus of that particular element. Thank you.